Okay, following on really from our integrated consideration, let's have a look at a differentiator. Okay, it's an inverting amplifier really configuration here. So what we'll do here is we'll see if we can find an expression for the current I1. So let's call this I1. And then let's call this current over here I2. We'll find an expression for that guy as well. So look, I1 is really equal to C dVC by dt. Now, providing this output over here is not in saturation, this is going to be a virtual ground over here. And so really the voltage across that capacitor is simply going to be equal to your input voltage. And so we can say that Vc is equal to Vin. And we'll put that into here. So we really say that I1 is equal to C dV in by dt. All right, now the current I2, let's look at that. Well, VO on this side, a virtual ground on this side, so VO is across R2. And so we can really say the current I2 is equal to VO divided by R2. All right, let's sum the currents going into this node. We've got I1 going in, we've got I2 going in. And so we can say I1 plus I2 is equal to 0. That's neglecting any current, of course, going into the op-amp, which is negligible. All right, looking at this expression then, we can say that I2 is really equal to a minus I1. Okay, putting in the values then for I2 and I1, we have VO over R2 is equal to a minus, putting in I1 here, this would be a C dV in by dt. So look, I could say in this case then that output voltage VO is simply equal to minus R2 times C dV in by dt. And so as you now can see that output voltage is really equal to a constant times the derivative of the input voltage. Let's look at another way we can actually determine that output voltage as a function of the input voltage. This time let's call this guy over here, we'll call it ZC. All right. Now, this is an inverting amplifier sort of configuration here, and so what we can say is that output voltage VO is simply equal to gain, so there's a minus sign here, that would be R2 over ZC multiplied by that input voltage. All right, let's look at the ZC. And so really from a Laplace point of view, we can say ZC is really a 1 over SC. Okay, let's put that information into our equation here. So we can say that the output voltage VO is really equal to, it's a minus R2. Let's put ZC in, well that's a 1 over SC term times V in. Okay. So what is that equal to? Well, you could say that's equal to a minus, we've got R2, bringing this up, we've got a C, and then this is an S times that input voltage Vin. Now what you can say here is that this, as a constant R2C, and this S over here implies differentiation. So it's differentiation of that input voltage. And so we really could rewrite that as we did before. That's an R2C, and that would be a dV in by dt. Now there is a little bit of a problem with this circuit. So let's have a look at this ZC really from a frequency point of view. Now look, we've said that ZC is equal to what? We said that was a 1 over SC, okay? Now from a frequency point of view, we can say S is equal to J omega. So rewriting this becomes a 1 over J omega C. So look, as this omega, as this frequency here goes up, what happens to this term over here? Well, this becomes a bigger number in the denominator part of this equation, and so this gets smaller and smaller. And as that frequency goes towards infinity, or a very big number, this ZC, what happens to it? It basically is going off towards a zero, a very, very low value. Well, let's think about that. What does this do really to the gain here? We can say that that output voltage, remember we said that was what? It was basically a minus R2, and that was divided by my ZC term over here times that input voltage. Well, if this is becoming very, very small, it means this gain term over here is becoming very, very large, and really it's going to force that output voltage over here towards saturation. So it's going to be clipped basically by the power supplies of the op-amp itself. And so this is going to go towards a saturated value. So that really is a problem in the case of the ideal differentiator, is that at high frequencies, this term here becomes a very small value, forcing this output voltage over here to actually go to a saturated value. A way to fix the problem is really to have a small resistance in series with that capacitor. And so we can now talk about the impedance of that resistor capacitor combination, which we'll call Z. We can then say Z is really equal to the resistor R plus the 1 over SC term, okay? Now, we need to have a situation whereby over our normal frequency of consideration, that this guy over here is really the dominant term. So this needs to be the dominant term over the normal frequency of our consideration. And so really, in essence, we can neglect this resistance, which is R1. We can neglect this resistance over here, and of course the output voltage then is simply a constant times the derivative of the input voltage over here. But in the case where our frequency, omega, tends to a very large value, or tends to, let's say, infinity, being a very large value, we can say that the impedance of the capacitor then, of course, becomes negligible, and the Z term over here simply will tend to that resistor R1. Now, our output voltage, V out, is then simply going to be equal to the R, or minus I should say, the R2 over the R1, and that would be multiplied by this input voltage V in. So we want to choose a value of R1. Yes, it's got to be small, such that during the frequency of operation or consideration, this is the dominant term. But if we do have frequency components that are very large, maybe noise or whatever else, then we want to make sure that the output voltage then is simply R2 over R1, this having a value such that this output does not go into a saturated condition. So this needs to be small enough really to avoid this output voltage going into saturation for a given input voltage value. And so that then becomes really a design consideration.